Hey there Polysthetics, welcome back to the Andromedoom devlogs, episode number 2. If you'd like to skip ahead to the content, please check the timestamps in the descriptions down below. I'm just going to be showing you how to set up keyboard controls for the player pad and the camera. And in today's devlog for the Andromedoom main project, I'm just going to be introducing you to the first batch of aliens, the Bathymetroids, the ocean-themed alien ships that will be invading the Asia-Pacific region. Now, although the game is intended for touch controls, mobile gaming only, I'll be doing the testing of the game on their desktop PC as I develop it. So setting up keyboard controls is crucial for the development process. I'll be picking up where I left off from the last tutorial. I'll give a brief rundown of the hierarchy, but I will gloss over some of the details. Alright, let's head over to the screen. Alright, well this is where we left off last week. In the hierarchy you can see the floor with the collision shapes defining the invisible walls. Got the lights underneath that spatial node, the camera origin, which is an empty with the camera object underneath it, the player node which we looked at last week, and the UI which we won't need for this tutorial. So on the player node, last week I created a script called player. I've renamed this to player movement. It's good practice to keep scripts and classes specific for one purpose. You should only change a class to change one thing. So step 1 is defining our keyboard inputs. Let's go to project settings, and then go to input map, the second tab on here. And as you can see, there's a whole bunch of predefined mappings, and each input event received in the input singleton gets mapped to a string which you pass as an argument into the static methods. Now by default you have a bunch of mappings that can't be removed because they're used by the Godot user interface. But it's a good idea to create your own strings, input event strings, and not use the default ones. Let's call these inputs move. And to add a keyboard input, you just select the plus button here and type physical key. So I'll be using the arrow keys for movements. Done. To map these to movements, just return to our script, and it's very simple. Now in the last tutorial we received joystick inputs and mapped it to an intermediate vector that ultimately gets passed into the move and collide function. The reason I created this intermediate vector is because I knew that I was going to be receiving keyboard inputs. So it's a good idea to decide what the precedence is. In other words, if we have a joystick input, we want it to override the keyboard input. If we have no joystick input, then we take the keyboard input. The way you do this is with the input singleton object. But let's put this in a separate method. Calling it keyboard movement. So we're taking the two values, the x and the z. So declare a new float, x. Use the input singleton. And the method we'll be using is getAxis. If you've used Unity before, you're familiar with this method. But you're specifying two actions, one mapped to -1, the other to +1. And so our negative action in the x direction is move left. And our positive action is move right, which is what we map to the left and right arrow keys respectively. And then we return new vector 3. We pass in the x, 0 movement in the y-axis, and then z in the z-axis. And here we reset the movement vector to get keyboard movement. Okay, let's test this. Good. However, I will need to reverse my up and down. They're working in the opposite direction. Now, when I was controlling the player, when I pressed the up arrow key, I was actually moving down the floor, and vice versa for the down arrow key. It's up to you how you want to fix this. You can reverse the mappings, but it's a good idea to stick with the conventions on the gimbal here, in which case that little control node, that is the forward direction, so the camera is actually pointed in the opposite direction. So in this case it would be better to realign the camera. Much better. Everything works as planned now. Now camera movements and rotations have their own little annoyances, which is why there's a lot of different ways of handling rotations in game engines, whether it be quaternions or basis vectors. I think it's best for limited applications like this. It's best to keep your solutions simple. So as you saw in the prototype, the camera moves up and down in the altitude, and it pivots around the player node, which is what you'd call an azimuth in astronomy. So the way I choose to solve this is by using two spatial nodes nested under each other. One that controls the azimuth, one that controls the altitude. So this camera origin node I'm going to rename to camera azimuth. And I'm going to add a spatial node underneath, which I'm going to call the camera altitude. And we're going to nest the camera underneath that one there. And it's a good idea, since the rotations will be carried by the other two nodes, to reset the node on this one. Reset the Y translation and reset the X rotation. However, keep the Z offset. That's the distance away from the center of the player pool. Alright, and to restore our old angle, we're gonna push this up by 30 degrees. Keep in mind the right hand conventions. Point your thumb in the direction of the arrow that you see, and then curl your fingers around. That's the positive direction of rotations. Now let's define our keyboard inputs for camera controls. Let's go into our project settings, our input map, and we'll create a bunch of actions. So camera up, camera down, camera left, camera right. And I'm going to map these to the W, A, S, and D keys. Oops. Attach a script. Let's put this in the script folder, and we'll call this script camera movement. First thing we need is to get keyboard inputs again. So let's just create a function for that. This only needs to be a vector 2, and we're going to do this the same way we did the player method we saw earlier. So float x, input, get axis, then we're going to return the new vector built from these x and y inputs. Cool. Now the x input is what we're feeding into the azimuth node, which is what this script is attached to, so no problem there. But the y input will need to be fed to the altitude node, so we need to cache a reference to that child. So we need to specify the type spatial for this node because we're using the transform property. We'll just call it altitude, altitude, and get the node, camera altitude. Now you need to cast this to the spatial type because get node returns a node by default. So you can say spatial. Alternatively, you can use generics because this function has a generic variant, just like that. Personally, I prefer the more human readable way, like this, using the as keyword. So now to move the camera, it's best to keep it in the physics process. The reason is we're going to be attaching the rotation of the player node to the camera. And in this context, it's best to keep it in the physics process, lest there be a mismatch between the frame update and the physics update. First thing we do in the physics process is get the keyboard input using the method we put together. So let's declare a private field, private vector2 called keyboard input. and every physics process step we get the keyboard input and store the values in the field. Let's show the rotation in the azimuth first before we do the altitude. So to do this, you use the rotate method, which is attached to this node. This takes two arguments. The first is the axis of rotation, which, because we're rotating about the azimuth, is the y direction. Note your right hand rules. Quite simply, this is just vector 3 up. This happens in the local plane. So if you're rotating about a moving object, you can always use vector 3 dot up. You don't have to use a global coordinate. And the angle is keyboard input, that vector we created, the x value. Let's test this. So this is A. You can see the camera's rotating. That's D. I'm guessing they're rotating in the right direction, but as you saw, they're rotating very quickly, and that's because we didn't account for the time increment. To fix this is very simple. You multiply by delta, and that's much better. And the rotations are correct too. Now the camera rotation is slow, so we should export a field to control that speed. Using the export attribute, we'll define a float, just call it a speed, and we'll just double the speed for now. To vary this field, first you can either press play and test it, or you can hit build. This will compile the C# scripts, and the field will come up here. There it is there. Okay, next thing we do is rotate the altitude. Now we've already got a reference here in the ready method, which is called on when this node enters the scene tree. And so to rotate that node is just a matter of typing the name and using the rotate method. Simple. Now again, keep in mind your right hand method. So our axis is vector 3 dot right. And the degrees will be the keyboard input dot y. As you can see, works perfectly well. However, we don't want to be rotating completely around the player. So it's a good idea to clamp the altitude values. So first, let's define a range of values that we want to clamp the altitude to. So we'll export a float array, and we'll call this altitude limits. And let's say we want it to go from 10 to 80 degrees. And let's call a method here. We'll call it clamp altitude. Now spatial nodes have a rotation degrees property, can set and get the current Euler rotations as a vector 3. However, to set Euler angles, you can't do it directly. So I can't say rotation degrees. Well, in this case, we're changing it on the altitude node. So I can't say altitude dot rotation degrees dot y equals, say, 5. Because y is a value, not a reference. So to fix this, we need to create a new rotation degrees vector that we then assign to the rotation degrees property on the altitude node. So we'll call it vector 3, new rotation, and we'll call the altitude node, and we'll get the rotation degrees property. Now this new rotation, we're going to clamp it, and there's an inbuilt clamp method. In Godot with C#, the class is called mathf, not math, that you may be used to in GD script. Mathf.clamp. Now it takes both integers and floats. Don't need to worry about that, the method's overloaded. So what are we clamping? Well, the new rotations, oops, this is actually X. And we're gonna clamp it between the altitude limits. And now the altitude node, its rotation degrees property is set to the new rotation. Okay, let's test this. And as you can see, you can't go past 80 degrees. And you can't go shallower than 10 degrees. Working as expected, very good. Now there's one other complication here. The player does not rotate with the camera. There's many different ways of solving this. And what it comes down to is how you want the gameplay to feel and how you want to scale up the project. So the last thing we need to do is figure out how we want to rotate the player in line with the camera such that the directions the player moves is always oriented with the direction the camera is facing. Now the way Godot works is with transformation matrices. So let's say this is the global origin, 0, 0, 0. And this here is the player's local origin. Now there's a 4x3 matrix, 3x4 depending on how you look at it, with 4 vectors. So the first one is what we call the origin. This vector represents the centroid, or the location relative to, well, technically relative to its parent. So if this node here was underneath its parent, let's say its parent was here, then the origin is actually this vector. But for the sake of argument, let's pretend this node doesn't have a parent. So that origin row is this vector here. Now you've got 3 other vectors, and what these do is define the rotation of the node. Together, these 3 vectors form what we call the basis. Rotating a node changes its basis vectors. So if we undo some rotation about the y-axis, we realign these basis vectors. Something like that. Now, notice how when we rotate this node, this origin vector doesn't change. So if we simply keep using the move and collide function, the movement does not respect the fact that these basis vectors has changed. So the proper way to handle movement from this point forward is actually to take our movement vector, so our relative movement, and multiplying it by the transformation vectors. I'll show you how to do this in code. So this is where we left off. Now in the last episode I showed you how to send and receive data between 2 nodes using the signal function. In this instance, all we're doing is sending a float, which is the rotation about the azimuth of the camera and now also the player node. So I don't think setting up a signal in this case is warranted. Instead, I'm just going to create a property on this player movement class. Now in theory, we could handle the player movement in the camera function just by getting a reference and then rotating it there, but it's not good practice. The camera movement class should only handle the camera movement, and the player movement class should only handle the player movement. So let's store a float, a private float. We'll just call it azimuth rotation. We could call it orientation, I guess. Yeah, we'll keep it as azimuth rotation here. We'll set its value to 0. And we need this field to be accessible. So we'll create a property for it. A public float azimuth rotation. Oops. Got to use Pascal case there. And when we just return the azimuth rotation. And when we set this property, and to set, we just set the azimuth rotation fields to the past value. Now let's return to our camera movement script, and we get a reference here to the player node, and the reference type here is player movement. And again, in the ready function, we get a reference to the player node. Last tutorial I showed you how to do this using the getTree method with the roots property. You don't actually have to use that. What you can do instead is use getNode, type in root, and player. And of course you need to cast it to the specified type, which is player movement. Cool. This is actually underneath level manager. Now every physics process, once we've rotated the camera, and we are going to set it to the keyboard input .x. Now to keep this neat and tidy, let us extract this method. Control full stop, or control period for Americans. We'll call this movement input. So every physics process, we get our movement inputs. We then rotate it by the azimuth rotation about the vertical axis, which is vector3.up. And this is where things change. We can't pass the vector3 movement in here. So let's pull this out. Movement times delta times speed. Now let's refactor this code a little bit just to make it a bit cleaner. So this movement input, we'll make it return the vector. Vector3, we'll default this to 0. And we'll return this output here. And we'll set our movement fields to the movement input. And here we can multiply it by delta and speed. And this cleans up everything a little bit. So our relative vector is going to be the current transform basis multiplied the x row. Going to multiply this by the movement vector, the x value of the movement vector, and whoops, transform dot basis dot z movement dot z. And that's our new movement vector there. Now I'm only putting the left and the right keys, but as you can see, the player pad is moving correctly. Even if it's in the corner, it always moves relative to the camera orientation. Now we're almost home. There's two minor issues you may have noticed. The first is moving left down, upright is fine. Moving diagonally, however, is a lot faster. And the reason for this is obvious. It's because we're adding two orthogonal vectors together. So the magnitude of that vector is going to be root 2. So we need to normalize it before we use that vector. And the second is, following along from last week's tutorial, the joystick's input has been reversed. Now there's a simple fix for the latter. You just put a negative sign there. Now the former complicates things a bit. The first thing we do is pull these out, the delta and the speed modifiers. We take this vector here and we normalize it. And we paste the time increment and the speed in there. Let's test this out and see what we've broken next. Great. See now diagonals. Looks like they're moving at the correct speed. this is what we've broken next. It's the joystick. Remember, the joystick responds to sensitivity. The pad should only be moving at full speed if the joystick is all the way to the corner. So the last step is fixing that. So let's cache a local variable, a local float. We're gonna call it, we should call it something more descriptive. So movement, magnitude. And this is equal to the movement and its length. So then to reset this magnitude, so multiply this original vector by the movement magnitude. Keyboard inputs look all okay, as does the joystick input. A sensitive movement causes a slow play and pad speed, and jamming the joystick to the edge moves the pad at full speed. Rotating the camera has no effect on the relative movement of the player pad, and the joystick has precedence over the keyboard input. Alright, well, thank you for watching that tutorial. I hope you took something away from it. If you have any suggestions on improving the code, please put them in the comments down below. Help out your fellow mates and help me out as well. In next week's tutorial, I'm going to be showing you how I pulled together the touch camera controls, and that one hopefully is not going to take as long as this one. Stick around if you'd like to see the aliens that I've put together for the first region in the Andromedoom game. Right, say hello to the Bathymetroids. These are the aliens you'll encounter in the first region, which is the Asia Pacific region. And as you can see, I went for the oceanic theme. This ties in with the Asia Pacific region, the Pacific part. And of course it ties back to the original Space Invaders, which were based on sea creatures. In particular, the crab, the squid, and the octopus. I introduced my little notebook in the last video. And here they are. And you see them here on screen. And I'll be covering in depth the design process I use for building themes, putting creative constraints on the designs, and how to pull together color schemes, etc, etc. But I'll dedicate a full video to that once I'm finished with the tutorial series. And so what we have is a bunch of pixel maps here. This is the color scheme, and here you have a texture atlas for the aliens I've put together. And I've got another map for the metalness. I'm going to develop this further, and if required, build a roughness map. Roughness maps, maybe bump maps, depending on how it looks on the small screen. So I'll show you the Blender renders. So here's the first crab I pulled together. It's quite awful. I think I was exhausted the day I built this. It taught me a few things. Now, in particular, with mobile games, we want to make our meshes as light as possible, so the minimum number of triangles, and small textures helps. Maybe not so necessary in modern devices, but I do like it. And so what this taught me is not to rely too much on complicated geometry to get the textures, to get the fine details right, and to rather use alpha textures. So here are the proper models. And the first one is the crab. Let's take a look at it in Blender. I'll show you what I mean. So as you can see, what might look like complex geometry on the surface, in the legs and the pincers, is actually 2 planes per leg, or in other words, 4 triangles. And I'll let the alpha channel of the texture do the heavy lifting. And you'll notice that the meshes themselves aren't closed, because in the game you'll never see the undersides of these models. But we need to make sure that we'll be switching off backface culling in the Godot engine, so that the undersides of these planes will be rendered as well. So here's the crab, and there's a sort of diesel punk panel steel ironclad ship aesthetic that I'm going for. I intend on building heavy themes for the aliens and also the player ships, because I don't have that creativity with the city buildings as much. Now everything will have its own particular color scheme, which I'll discuss in detail in the future. So let's look at the next one, and that's the octopus. Again, one of the original characters of Space Invaders, and the third one is the squid. And so the intention with the squid is to make it a character that can ink the player, much like in Mario Kart. So you'd get ink splodges on your screen, which would obscure your vision. Now these first three characters will be spawning on the first level, which is Sydney. But as you progress through the other 5 levels in the first region, a new character will be introduced each time. And first one is the shrimp. These are like little fighter jets. They come in swarms, but they don't land. And their antenna are actual radio antenna. The 5th character is the stingray, which is similar to the UFO of the original Space Invaders. Again, it won't land, but it will fly over from the top and pack a big punch if you're not careful. The 6th character is the man o' war. It's got that little submarine aesthetic and the antennas there, and this character is a drone that detonates itself. So this long tentacle here is like a fuse, similar to a daisy cutter bomb, and if you let it land, it will detonate. Our 7th character is a goblin shark. Again, as you can see, it's got a big smokestack, and this is kind of like a mini boss. It packs a heavy punch, it lands, and it's quite tough to take down. And the final boss is Leviathan. This is not the complete length, and this will be the adaptation of the boss that you saw in the prototype, which is based on Terraria's Eater of Worlds. So there will be multiple middle body segments with tails and heads, and if you hit a segment and split the worm in 2, you get a second head. Again, you can see the industrial maritime aesthetic there, the smokestacks there, the warning stripes, the Godzilla inspired head. Godzilla? Yeah, I don't know. Well, that's all I had for this week. Thank you very much. In the next episode, I will be showing you the city buildings that I will pull together in accordance with my program. If you have any questions, comments, suggestions, please put them in that little box down below. If you're enjoying this video series, please share around, hit the subscribe button and the bell as well, and I'll see you in the next one. Thank you guys.